5 approximation for every cardinality. And with that in mind, one can perhaps redefine this concept in using a two-player game. So you can imagine that there are two players, so one is Alice and Bob, and Alice wants to select a matching, and Bob wants to select a cardinality. And what's the profit, or what's the payoff that Alice received? Well, it's just the ratio between the weight of the top k edges that of her matching compared to the optimum of compared to opt k. So the payoff is always a number between 0 and 1. And what is, in this context, a robust matching? Well, a robust matching is just a matching that Alice can play that allows her to, or guarantee her to have a payoff of alpha, at least alpha. Okay? So the same example as before, this blue matching is 4/5 robust. If Alice plays this matching, it doesn't matter what k selects Bob, what k Bob selects, she will get at least a payoff of 4/5. So that's the definition that I need to explain our results. So is the game clear?
It should be always the heaviest map.
Yeah, so you always select.
But you can select a subset of k.
Yeah, but if you select a subset of k, then it would be worse. So yeah, so you have to select the top k edges. Okay, so the top k edges. Good. So with that in mind, one can define the matching robustness of a graph, of a weighted graph, as the largest alpha for which there exists an alpha robust matching. Okay, so in the previous graph, this was 4/5. So that would be the robustness. It is known that computing the robustness of a weighted graph is NP hard, and also that it's very easy to get a half robust matching. You just have to select the greedy matching. So the greedy matching is this matching that you create by selecting the largest edge first, the heaviest edge first, then you select the next heaviest edge that you can add to your matching, and so on. That's the greedy matching, and that's always a half approximation for every cardinality. So in particular, it's a half robust matching. So the robustness of a graph is always between half and 1. Okay? Because the greedy is always a half solution with robustness half. So, but on the other hand, there are some graphs for which this number, so this robustness, is 1. Okay, so for example, if you take a matching, so if the graph itself is a matching, you can output this matching, and that would be a 1 robust matching, because for every cardinality, this matching contains the optimal solution. So here is an interesting case. So if you look at this 3-edge graph with weights 1, 1, and square root of 2, it's very easy to see that if you want to output if you want to find the robustness of a graph, or the robustness of this graph is achieved in a maximal matching. So you have to select either the 2 vertical edges or the horizontal one. Okay, but here it's very curious what's going on, because if you select the vertical edges, then this matching is very good for cardinality 2. For cardinality 2, it's the optimum. But for cardinality 1, so if Bob plays 1, then Alice only gets a ratio of 1, so the top edge of her matching, over square root of 2, which is the optimum of 1 edge. So for the vertical matching, you have a robustness of 1 over square root of 2. And for the horizontal matching, so only the top edge, that's also the ratio that you get. You also get 1 over square root of 2. And the reason is that, this edge is very good for cardinality 1. It's the optimum. But for cardinality 2, the ratio that you get is square root of 2 divided by opt2, which has a value of 2. So square root of 2 over 2, that's 1 over square root of 2. So in this case, you have a robustness of 1 over square root of 2. And why is this example interesting? Because this is actually the worst example. So there is a theorem by Hassing and Rubinstein that says you can always compute a matching that is this number robust. So the minimum of 2 to the minus 1 over p and 2 to the minus p minus 1 over p robust. But it doesn't matter what this formula is, but if you put p equals half, equals 2, you can always get a matching that is 1 over square root of 2 robust. And the matching is obtained it's very easy to get this matching. So the only thing that you have to do is you have to take all the weights of your graph, square it, so raise them to a power of 2. So for example, in this graph, you would get the central edge would become 2. So you square the weights, and then you go compute a maximum weight matching there. That object is, if you go back to the original weights, that object is 1 over square root of 2 robust. So so this theorem essentially tells you the worst example is this 3-edge graph. So this is the graph that has smaller robustness. Everything else is between 1 over square root of 2 and 1. Okay, so that's the background. So that's the story of the problem that I want to study. And now let me tell you what did we do. Okay, so what's our work? Okay, so first of all, the original proof of Hasin and Rubinstein was a little bit complicated, so we gave a new LP-based proof of that thing. So every graph has a 1 over square root of 2 matching. So we gave a new proof of that fact using LP, linear programming. Another thing that we did is that we extended the notion of matching robustness to a random one, so to distribution over matchings, and that's I'm going to talk about that next. And we know, so essentially what we did is that we proved that if Alice is allowed to randomize, then she can beat 1 over square root of 2. So she can get more profit. We gave some extensions to other problems, not just matchings, major intersection, V-matchings, and other problems. And we also extended to a version that is asymptotically, an asymptotic version of these problems, which if I have time, I will explain what that is. Good. So here it's, so I'm going to focus on this in this talk. So I'm going to only focus on these two, and then if I have time, I will talk about asymptotically robust matchings. So let me tell you what a robust distribution is. So an alpha robust randomized matching is a weird name. So it's just a distribution over matchings of the graph. That is an alpha approximation for every k in expectation. So another way to put this is that play the same game as before, but now Alice can randomize. She can select a distribution over matchings. And then Bob selects k, and then the payoff is just the expectation of this ratio, of the ratio between the weight of what Alice gets and the optimum. Okay, so it makes sense that if you allow randomization, this thing could get better. And of course, you can define now what's the randomized matching robustness. So you can define what's the largest alpha for which there exists an alpha robust distribution now, not just a matching. And trivially, this number should be at least as large as mu, as the deterministic robustness. And it's at most 1. Okay, so there are a few questions that now one can ask. For example, can mu star be 1? Mu star can be 1. So if the graph itself is a matching, then mu star is 1. Mu star can be equal to mu in that case. Another example, so what happens with this 3-edge example? So with this 3-edge example, one can show that, well, Alice can now randomize. So she can output, for example, a convex combination of these two matchings. So she can select this matching with probability half and this matching with probability half. And it's very easy to see that if she does that, then the expected ratio for k equals 1 and the expected ratio for k equals 2 are both the average between 1 and 1 over square root of 2. So this number here, it's better than 1 over square root of 2. So this, in this particular graph, I've shown you that mu star can be strictly larger than mu, because for this graph, mu was 1 over square root of 2. Okay? So mu star can be strictly larger than mu. So is the definition clear? The definition of robust matchings. Any questions so far? Okay. So it's the same thing as before, but now we allow Alice to randomize. We allow Alice to select a distribution over matching, or select a matching at random, essentially. Now, so here are the questions. So the natural questions. We know that mu star is larger than mu. It's at least as large as mu. But is it always true that mu star is strictly larger than the lower bound of mu? So is it true that mu star is strictly away from 1 over square root of 2? That's one problem. And another problem is, can we always find a randomized matching with robustness at least 1 over square root of 2? So that should have been a mu star. So with the randomized robustness, at least 1 over square root of 2. And our result is that we can always do that. So we can find, we have a polynomial time algorithm. It's a randomized algorithm that returns an alpha robust randomized matching. So it returns a distribution, or in other words, it's a randomized algorithm. So every time that you run, it outputs a matching. And the distribution of the output is the distribution. And for that particular distribution, the robustness is strictly larger than 1 over square root of 2. So that's the main result. For every graph, for every weight function. Right, so for every graph and every weight function. So let me explain how this works, because this is not, so it's not hard to explain, but it requires you to understand the notion before. So what's this notion I need is the notion of a Lex-max matching. So suppose that you're given a weight function, so the graph is weighted. A matching is going to be called Lex-max if you look at the vector of weights. So if you sort the weights from larger to smaller, if that string is lexicographically maximum. So in other words, if this matching that you have has the maximum number of edges possible of the largest weight available, so in this case 10, so it has to have one edge of weight 10. And then given that it has one edge of weight 10, it has to select the maximum number of edges of the next available weight as possible. So here it cannot select 9. So the next available weight, then it's 9, but it has to be, it cannot select it. So for the next one, which is 6, it has to select the largest number of edges as possible, and so on. So in other words, if you just write the string of weights that this matching has, so 10, 6, 6 is the string that is lexicographically maximum. Okay. It's very easy to compute Lex-max matchings efficiently. Just think of, so we want to have as many 10s as possible. So you could imagine that you put a virtual weight of n to the 10 or something like that. And then a virtual weight of n to the 9 to the next edges, a virtual weight of n to the 6 to the next, and so on. And if you compute, if you let n to infinity, if you let n go to infinity and you compute a maximum weight matching for that, that's going to be Lex-max. I mean, it's a way to do that. So you can compute Lex-max matchings efficiently, and well, they are not as bad as they look. So for example, they are not as bad as for this problem. So if you look at the weight of the top of L1, so if L is the Lex-max matching, if you look at the weight of L1, that's 10, which equals the optimum of one element. The weight of L2 is 16 in this case, and up to is 18, and so on. So these numbers are close. So these numbers are close. So we want to use that, and we want to do it in an interesting way. So this is the first tool that we need. The second tool that we need is the concept of a Witt function. So what's a Witt function is just a function, a weight function, such that all the non-zero weights are powers of 2. So you can have 0 weights or powers of 2. It doesn't. They don't have to be positive powers of 2. So they could be 1/2 or 1/4. So they can be 2 to the minus some natural number. But so in this picture, I draw the Lex-max matching for this graph that has only weights that are powers of 2, and something curious occur. So if you look at the weights of the top edge, of the 2 top edges, 3 and 4 edges of this maximum, of this lexicographically maximum matching, they coincide with the optimum. So in other words, this matching is one robust. It's good for every cardinality simultaneously. So the optimum matching with cardinality 2, let's say, has a weight of 10, for example, 8 and 2. Yes? Yes? See, Lex-max. Which 10 I select?
Okay, but if you had another edge of weight 10,
yes,
and selecting that edge of weight 10, you could select the edge of weight 9.
Then you have to select that other weight of the weight 10. Yes. 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 So you have to select the one whose string, I mean, the string of weights has to be lexicographically maximum. So in that case, if there is a way to select a 10 that allows a 9, then you have to select that 10.
If you could select 2 10s,
then you have to, you have to select 2 10s, right? So essentially you just write the weights W1, W2, W3, sort from larger to smaller, and then you want this string to be lexicographically maximum.
Okay, so there is only one, like every Lex-max matching induce one string.
Yes, every Lex-max matching has the same string of weights. Okay, so here this is W1. So, and the matching has weights, well, W1, W2. So that's the definition. Good. So as I was telling, if the weights are powers of 2, we realize that. So this is something that we realize. Lex-max matchings are one robust, and actually that's true. That's our first lemma. For every weight function, for every bit function, so they have to be powers of 2 or zeros, Lex-max matchings are one robust. Okay, so I'm going to try to explain this lemma for matching, for any Lex-max matching. So all Lex-max matchings have the same, so it's the same string of weights. So essentially, and the string of weights is what defines the weight of LK. So it's true. Any Lex-max matching, it's one robust. Okay, so that's the main lemma that we're going to and this lemma is not as hard. It's not hard to prove. So I will try to do it. So, but first, let me tell you why this lemma is interesting. Because for us, this lemma implies the theorem. So what was the theorem? That the matching robustness, so mu star, so the randomized matching robustness is at least 1 over ln of 4, logarithm base E of 4. And so here's the algorithm that outputs a distribution whose robustness is at least 1 over ln of 4. The algorithm is very simple. So just select a number x in 0, 1 uniformly at random. And with that number, define this weight function, this modified weight function, which is, so it's 2 raised to the power of logarithm of the weight minus x, and that's the floor of that. So it's very hard to parse. So let me maybe mention what it is. So if x is 0, what you're doing is you're rounding every weight to the power of 2 that is immediately below it. If x is a little bit larger than 0, you could round it to maybe the next one. Okay, but in any case, for every x in between 0 and 1, you either round the weights to to the largest power of 2 below it or to the second largest power of 2 below it. Okay? So it's just a little bit. So essentially what you're doing, we're rounding to power of 2, but we're doing it in a clever way. Why is that? Why do we want to round it to power of 2? Because we know that for powers of 2, you have 1 robustness. Okay? So the algorithm is very simple. So you just choose X, modify the weights, and then output a Lex-max matching with respect to these modified weights. Okay? So I don't have an example that, but perhaps is. So for example, if you select X equals to 0, essentially what you're going to do is you're going to replace this 10 by 8, this 10 by 8, this 6 by 4, and so on. If X is close to 1, then perhaps some of them will jump to powers of 2 below. No, it will happen. So for example, if it's 2 to the power of log base 2 of that, so it's yes, it's a little bit more complex. But let me tell you why this works. So it's a little bit of algebra only. So you don't have to follow all these details. So let me tell you essentially how we prove now. What we prove. So fix a number k. What's the expected weight of the matching that they return? Well, the expected weight, it depends on this number x. Okay, but now the expected weight, the original weight is related to this modified weight. You can show that the original weight is at least the modified weight times 2 to the x. That's just by the definition. And then by the lemma, by this lemma that Witt functions, so for example, this is a Witt function, are 1 robust, this tells us that for this matching is 1 robust. So that means that the modified weight of this matching is at least the modified weight of any matching of cardinality k. In particular, the weight of the optimum of the original problem. Okay? So that's the only place we use the strong lemma, and then it's just a little bit of algebra. So so this is an expectation, just by linearity of expectation. This is just the sum of all the edges in the optimum of that quantity over there, and then we have this equality, which is not easy to parse, but it's true. So you just replace the definition of Wx that is above, below. You take away a weight of E. You take outside the expectation a WE. So you have to add a 2 to the minus log base 2 of WE to the inside this parenthesis. And then what you realize is that this quantity over here is just expectation of 2 to the minus U, where U. So this number over here, so this is the floor of a number minus this number. So this is a number between -1 and 0. And actually, because x was chosen uniformly at random, you can show that this is actually the expectation of 2 to the minus u, where u is a uniform random variable in 0, 1. And that's where the logarithm base 2 comes from. Okay, so it's not so complicated, but I wanted to just show it in the screen, the entire deduction. Good. Yes?
Do you have any?
Mm-hmm.
When do you need the X? So just to construct a distribution.
Yeah, I need to do a distribution, because if you do it deterministically, if you just round it to the next power of 2, you will lose something. So for example, because you have to. So it's very easy to see that the modified weight is 1 robust, but then you have to go back to the original weight. You have to say the expected weight, the expected original weight of what you get is at least some constant times the weight of the original optimum. And the weight of the original optimum, if you just round to the next power of 2, will be, you have no control. It could be a factor 2 away. So you could lose a factor of 2. So if you don't do it, if you do it deterministically, you could lose a factor of 2, and you don't want to lose this factor of 2. That's
But
the.
you can also,
Mm-hmm. Yes.
probably you can choose not only a different distribution
Yes.
for the x, and that gives you different
It could, yeah. So we tried to play with this a little bit, and we couldn't find a better distribution. So we couldn't find a better distribution. We're not sure if I'm pretty convinced it's the optimum, but I don't have the proof. So, okay. But essentially, the main idea is try to round in a clever way to a powers of 2, because for powers of 2, this problem is easy. That's the essential idea. And now let me just show you why for powers of 2 this problem is easy. Okay, so what we want to prove is that Lex-max matchings are one robust. So let me show something weaker. Let me just show that Lex-max matchings are matchings of maximum weight. So this is good for the largest cardinality available. So they are good for the largest cardinality available. And actually, these things are equivalent. And let me tell you why. So suppose that you want to show that the strong lemma holds using that the weak lemma is true. So do the following. Choose a k, choose a number k, and then compute a Lex-max matching in the graph. And let M to be the optimum with k edges. Okay? And now compute the graph that has as weights, as edges, Lk and M. Okay? So in this graph, you only have edges from the top k edges of L and edges from M, from the optimum. Now, in this particular graph, if you choose M carefully, and I'm not showing you why, but if you choose M carefully, so among all the optimum, you select one particular optimum, you can show that Lk is Lex-max. Okay, it's very natural. So the prefix of L should be Lex-max, and that's indeed the case. But in this reduced graph, you can now apply the weak lemma. Weak lemma says, well, the Lk is Lex-max, so it has to have maximum weight. So the weight of Lk has to be at least the weight of the optimum in this small graph, which is M also. And now you have that the weight of Lk is at least of k, which implies that L was a 1 approximation for that cardinality k. Also, since this is for every cardinality, we're done. So we showed that the only thing we need to prove is this weak lemma. So we only need to prove that if you have a Lex-max matching, then that matching has maximum weight. But that, so, and that I'm going to do it by, so here I'm going to do a picture, maybe here. So what do we want to prove? We want to prove that if you have a bit function and you compute a Lex, so let W be a bit function, and without loss of generality, assume that the graph is complete. Otherwise, you add zero weight edges. It doesn't change the proof. Now, and even more, assume that the graph has an even number of nodes, because I want to work with perfect matchings, just for simplicity. So compute a Lex-max matching and compute a maximum weight matching, M. And among all the maximum weight matching, select the one that has smallest intersection possible with L. Okay, so just that can be done. And now, since both matchings are perfect, why is that? Because if they were not, you can always add zero weight edges to complete the matching. So if both matchings are perfect, then the symmetric difference is just a collection of cycles, alternating cycles. So you have two matchings, the black one or the blue one and the red one. And what you have is a collection of alternating cycles, so edges of L and M. And what I want to show is that in every cycle, the weight of L intersected that cycle equals the weight of M intersection that cycle. That's what I want to show, because at the end of the day, what I want to show is that the weight of L is equal to the weight of M. So I want to do it for every cycle. Now, here's the interesting claim. In each cycle, So I drew one, I drew it on a line over there. In each cycle, every edge is, no edge is strictly larger than both their neighbors. So you cannot have a situation like this. For example, this, remember the weights are powers of 2. You cannot have 8 and then a 4 and a 2. You cannot have an edge that is larger than each of the neighbors simultaneously. So that's the claim. And the proof is very simple. So let's call this central edge E, F and G the other two. And notice the following. Suppose that this edge have weight strictly larger than F and strictly larger than G. Then, because the numbers are powers of 2, you also have that the weight of the central edge is at least the sum of these other two, because each of the other is at most the weight of E half. Okay, so that's the only place in which we use that things are powers of 2. Okay, so this line over here. So the weight of the central edge is at least the sum of the two weights, and now we have two possibilities. Either the central edge is part of M, so of the maximum weight, or part of the lexicographically largest matching. So let's assume that the central edge is part of the maximum weight. But then that's a problem, because what you could do is you could take L, the original matching L, remove F and G, and add the central edge E, and this new matching, L prime, it's a matching. It's not a perfect matching. It's a matching. Just take the original matching. No, L prime. So take the original matching L, remove these two edges from L, and add this one. This one. I mean, it cannot intersect any other edge of L, because the only edges of L that it intersected was F and G. So this new thing is a matching, and that's it. And that's a contradiction, because this new matching L prime is lexicographically larger than L. You added an edge of larger weight that was not there before. So L prime is lexicographically larger. So this thing here is lexicographically larger than L, which is a contradiction, strictly larger than L, because L was Lex-max. And the other possibility is that the central edge was red, so part of the part of L, of the lexicographically larger matching. But then you do the same thing. Take the matching, take the maximum weight matching M, remove these two edges, and add the central one. The central one has weight at least the weight of these other two, the sum of the other two. So what you get is a new matching with weight at least the weight of the original one. But then that's a problem, because that means that this new matching is also optimum, maximum weight, but it has smallest intersection with L. So that's a contradiction. So what we have shown here is that for every edge in a cycle, it's not possible that this edge has larger weight than both. Or another way of saying, there has to be a neighbor that has weight at least the weight of E. So there has to be a neighbor of weight larger or equal than E. But that's strange, because if you look at what's going on here, then one can show that in every cycle there has to be two edges of the same weight. And why is that? I mean, just take the maximum weight edge of the cycle. The maximum weight edge of the cycle, because of what we have shown, one of the two neighbors has to have weight larger or equal than its weight. So one of the two neighbors has to have the same weight of the maximum, so as the maximum weight of the cycle. So that means that there are two edges of the same weight. But that's good, because we want to show that the weights of the cycle of the cycle intersection L and the weight of the cycle intersection M are equal. So we know that these two edges have the same weight. So that's progress, because now what you can do is you could contract these three nodes into a single node. So you could contract E and F. You could contract these two edges of the same weight and repeat. You would have new cycles for which all these properties that I showed before holds. I mean, this proof is a little bit more complicated, but it's essentially the same. And in this new reduced cycle, you can show that there are two edges, one black and one blue and one red of the same weight, and so on. So with that, we have shown that for every cycle, the red weight of the cycle equals the blue weight of the cycle, and that's with that we conclude that the weight of the lexicographically the Lex-max matching is actually maximum. So we're good in time. So this is the summary. So we shown that. So we just shown this weak lemma. So we showed that Lex-max matchings are maximum matching, maximum weight matching. We showed that this implies this strong lemma. Lex-max matchings are one robust. That this implies the theorem that the robustness is at least 1 over ln of 4 by rounding. And the good thing is that this is true. I mean, one interesting thing is that we did this proof for matchings, but then we realized that we don't need to do it. We don't need to assume that the objects that we're working with are matchings. So as long as the weak lemma holds, this proof go through. So if you had another problem in which you are computing robustness against cardinality, okay, then and the weak lemma holds, in that particular problem you can define the robustness and you can define everything as before. You would have mu star is at least 1 over ln of 4. And just for completion, I want to tell you what are these objects. So we've shown the following. So this is the extension. Okay, so imagine, so maximum weight matching can be cast as an instance of the following problem. So suppose that you have a collection of objects, E, like the edges of a graph, and a collection of subsets, I. Okay, so E comma I is called an hereditary system if whenever you have a set in I, so think of sets in I as matchings. Whenever you have a matching, then every subset of it is a matching. So that's what hereditary means. Okay, so every feasible set for the problem, every subset of it is also feasible. And suppose that you had a weight function on the object E, and with that you can always define this function opt. So the maximum weight independent set of cardinality. So opt k would be the maximum weight independent set of the maximum weight set feasible set in this family of cardinality at most k. That's opt k. Whenever and what's the nice result? So whenever you have a system and a weight function that satisfies that this function opt is concave. Okay, so opt concave means that it means exactly what's written over there. So opt of k is smaller or equal than opt of k plus 1, but the marginal increase increases over time. So whenever you have a function like that, so whenever you have a situation like that, for every big function, so whenever opt is concave for every big function, Lex-max sets are maximum weight sets, so the weak lemma holds. So the strong lemma also holds, and we have our results. So I'm not going to show how this is proven, but at least I want to tell you that there are interesting examples. For example, a matrix intersection. So intersection of two matrices is a concave system. V matching. So V matchings is a generalization of matchings in which every vertex has a bound, right? So you want to find a subset of edges such that the degree of every vertex in this subset is at most B of this vertex. So when B is equal to 1, you recover matchings. Strongly based order or matrix matching. So these are other problems of which this property holds. And for all these you can find a 1 over ln of 4 robust distribution. So just to mention one. So for example, matrix intersection, this is very nice. So suppose that you want to find, you have a graph. Suppose that you have a graph and the graph is colored. So the edges are colored. So there are k colored. It doesn't matter how many. And now what you want is what are the feasible sets? So the feasible sets are forests, so things that have no cycle, such that every edge has a different color. So a rainbow forest. So when the feasible sets are rainbow forest, you can play this game. So Alice selects a rainbow forest and Bob selects cardinality, and you can show that this is that Alice has a randomized strategy that gives her a 1 over ln of 4 revenue. So I'm not going to show you this, so that the concave systems that for every concave system you have the weak lemma. The proof is in one slide, but anyway, I won't show it. But what we want to conclude is with some discussions. So what did we do? So we partially extended this notion of robust matchings, which it was known before that you can always find a robust matching of robustness at least 1 over square root of 2 by Hassing and Rubinstein. We did an extension to randomized, so to the randomized version, and not only for matchings but also for other systems for which it was known that you can get a 1 over square root of 2 robust set, feasible set. So matrix intersection, it was known that you can get a 1 over square root of 2 robust independent set in 2 matrices. So what's open? So we know that the robustness of a graph is at least 1 over ln of 4. But we don't think this is tight. So we actually think that the worst example is this 3-edge graph. So we think that the right answer should be mu star is at least the average between 1 and 1 over square root of 2, but we haven't been able to show that. So that's open. And another thing is that we're not completely sure is that perhaps computing for a given graph and weight, perhaps computing the robustness is polynomial time solvable. We don't know. It could be. We think not. It's related to an NP-hard problem that we have seen before, but it's not easy to make the reduction. So so that's still open. And essentially that's it. Yes. Was the deterministic one. Deterministic one. So with that, I'm done. So the only thing so if I have 1 minute, I would like to just tell you what this concept of asymptotic robustness, but just tell you what it is, nothing else. So for robust matching, we showed that. So what's a run for robust matching is a matching such that if Bob selects any k, you get a payoff of at least alpha. An alpha j robust matching is one matching that if Bob selects any k larger than j, you get a payoff of at least alpha. Okay, so you want to force Bob to play only large cardinalities. Okay, what is an asymptotic? What is we shown, and this is the last result. So we showed that if you're playing this alpha j robust matching game, so if you're allowing Bob only to select large matchings, then Alice can select a matching deterministical matching, not a distribution that almost achieved this 1 over ln of 4. So essentially, the bad examples are only for small cardinality. Okay, so the exact statement is the following: for every epsilon. So if you want to get a matching that has robustness 1 over ln of 4 minus epsilon, there exists a number j such that if Bob only selects matchings of size at least k, cardinalities of size at least j, then every graph has this robustness, and we can find it. Okay, so with that, I I finished. Well, thank you.